Well, pre-calculus classes, as always, good morning, good afternoon, or good evening. What we're going to do with section 1.6 is, now that you guys have completed your project, just do a little bit of kind of quick wrap-up of 1.6. Just make sure to clarify any points that you maybe did or did not find as you were going through the project. So, we'll talk about shifting, reflecting, and stretching, the three basic transformations that you guys were looking at. So, if we have, for this first example here, h of x equals x squared plus 2, what is the parent function? Well, the parent function is h of x equals x squared. Same thing over here for the g of x equals x minus 2 squared. Your parent function is also x squared. So, as far as that goes, I will quickly sketch that and do that on both grids here. Hopefully you guys are at the point where you pretty well know those basic parent functions as well. Well, when you have a constant value being added or subtracted at the end, that's where, if it's f of x plus c, this is going to shift up to. Had it been minus 2, then it would have shifted down to. So you can literally just take all of these points and shift up 2 units. Well, likewise, these two down here at the bottom, when you have a quantity squared where it's x minus c, so like here, x minus 2 squared, that's going to move it right 2. Had it have been x plus 2 quantity squared, then it would have shifted left 2. So you can again just take all of those points and shift right 2 units. So again, those are your shifts of a parent function. Again, just as far as a couple of other shifts here for this one, your parent function, because this grid is not exactly very large, I'm only going to be able to graph 3 of the basic points. So for your cubic, you can at least get that shape in there. And again, this is going to move minus 3 down 3. And from there, like that. For this one, again, I will quickly sketch my parent function. And again, the minus 2 is going to shift it right 2. The minus 1 outside is going to shift it down 1. And so from there, you have, let's see, let me use the red. So here I'm just going to write 2 down 1, write 2 down 1, is that. So, reflections. Well, if you have an x-axis reflection, you have the negative out in front of your function, whereas if you have the negative inside the function, that's going to reflect it over the x-axis. And so these graphs here, I'm not exactly sure what these are going to be for, but if we skip over here and look at, the difference on the reflections using what was actually even here, g of x equals the opposite of the square root of x. Well, this is going to be the x-axis reflection. I use, r sub x, x-axis reflection there. If you have g of x equals the square root of the opposite of x, that's an example where the negative is within the function, so that is a y-axis reflection. It is possible to have a reflection, certainly, and a shift as well. So here you have a reflection over the x-axis. The x plus 2 is going to shift it left 2. Even though this is horizontal, this is vertical, I always like to do my horizontal shift first, then reflect over the x-axis. And this is where we'll even talk a little bit about, does the order matter if you have f of x equals x squared? Well, again, I can even quickly sketch in a parent function here. If you reflect over the y-axis, shift it up 3, does the order matter there? Well, no, because with this being a y-axis reflection, that reflects onto itself, and so whether you move it up 3 first or whether you reflect it first, because again, a y-axis reflection is horizontal and up 3 is a vertical shift, there your order does not matter. So here, order does not matter. And, the parabola will look like that. Well, if you reflect it, and again, we'll use the exact same x squared parent function. If you reflect it over the x-axis, shift it right 4. Well, if you reflect it over the x-axis, you end up with this, and then if you shift it right 4, so here's what I'm going to do, just kind of as my in-between, be a little ways off of the grid. Well, even if we would have shifted first, then flipped it down, no. The order again wouldn't matter because this is a vertical reflection, horizontal shift. So again, order does not matter there either. If, again, we'll use that exact same parabola parent function here. If we reflect it over the y-axis and shift it right 4. Well, of course, if we're using the parabola, in theory, because you reflect over the y-axis, the order here doesn't exactly matter, but that's also only because you happen to have an even function. So here, order does matter. And so you want to do right 4 first, then reflect over the y-axis. So that's why it's kind of like, here, if, you reflect over the y, then shift it right 4. So yeah, that's why, here if we shift it right 4, then reflect that, puts you over here. So 4 back there, and just like if you have this one where we're reflecting it over the x-axis and down 2. So here you want to go right 4, then reflect over the y. And I know that just different books that I've initially taught out of, some books use capital R. The book I initially taught out of used capital R as a rotation, so that's why I always use lowercase. It's fine either way you choose to do that. So here, if we have our parent function one last time, again, if you would move it down, then reflect, that puts you up here. When you have a vertical reflection and a vertical shift, you need to reflect over the x-axis first, then down 2. And so I will include kind of my in-between, then down 2, and those will both be a little ways off of the grid. So the main thing when you work with these, reflect over the x-axis before a vertical shift, do a horizontal shift before reflecting over the y-axis. I will always do a horizontal shift first, then any reflections, and do a vertical shift last. So give the order you would perform transformations for negative x squared plus 3. Well, again, this negative is going to reflect over the x-axis, then up 3. For what we call non-rigid transformations, meaning the shape is not changed, shifts and reflections are rigid. The shape doesn't change. Non-rigid transformations are those with what's called a distortion, meaning a stretch or shrink. If you multiply a number in front of the function, where c is greater than 1, that is a vertical stretch. If it's between 0 and 1, that's going to be a vertical shrink. If you have a number multiplied within the function, if it's greater than 1, that's going to actually work in opposite and be a horizontal shrink. If the value is between 0 and 1, that will actually stretch it horizontal. You don't see this used a lot until next semester when we start working with some trigonometric graphs, graphing some sine waves, but that's why we do go ahead and include this even now. So, to just finish up a couple of things here, again, our absolute value parent function is going to look like this. Now, when you have a value out front, this is going to be a vertical stretch. The way I always like to say is when you have a vertical stretch, basically all you're going to do, that's going to multiply the y value of your function coordinate. So right here I have a point at 1, 1. The stretched point will be at 1, 4. So again, instead of 1, 1, my new point is at 1, 4. Notice the x value doesn't change, only the y value does, just like over here. I have a point at negative 1, 1. Well, when I multiply the y value, my transformation point is at negative 1, 4. Again, the x values, though, don't change. And certainly there, the only one that's going to even fit is that first point. Again, if we come over here to this one and use, again, same parent function, well, again, 1/4 x, well, here, because it's going to be a little easier to see, I'm going to actually use the 2, 2 and negative 2, 2. Well, again, my x value is not going to change. If I take 1/4 times 2, that's going to be 1/2. So it's, and then same thing here. I'm still going to have 2, 1/2, negative 2. Again, the x values haven't changed. My y value does. So that's how you can work with a vertical stretch or shrink. Now, when you have, again, the horizontal ones, because that 2 being inside the function does technically make it a horizontal stretch or shrink, although with absolute value, you could move the 2 out to the front and work it that way. But what we will do is, just so you guys can actually see how this works, if you have a value inside of the function greater than 1, this is going to be a horizontal shrink. So again, for this one, probably going to be easiest to see if I use the 2's. Well, again, I am going to now only work with the x value. I'm going to divide by 2. Well, if you take negative 2 divided by 2, it's negative 1. The y value does not change. Here again, take the x value divided by 2, 1, 2. So that's why, yes, it looks like it is a vertical stretch, but where the 2 is, it does technically get classified as a horizontal shrink, just like here. If we use this one now, it's kind of going to be just as easy to use either of these, but basically, we can use the negative 1, 1 and the 1, 1. Well, this is going to be a horizontal stretch because now what we're going to do, if you take either 1 divided by a half, you end up with positive 2. If you take negative 1 divided by a half, you end up with negative 2. The y values, though, do not change. And so you have 2, 1, and negative 2, 1. So once again, those, it does, yes, the horizontal stretch does look a lot like a vertical shrink, although where this value is for certain functions will actually, matter. Again, more so when we get into trig next semester, but we do at least want to, as I mentioned, show you how the horizontal stretch and shrink actually work. So again, that's kind of a fairly quick wrap-up of everything that you looked at for your project in section 1.6.